Okay, so we have been doing nomenclature of carboxylic acid, so including aromatics or alkanes, aromatic cycloalkanes with carboxylic acid functional group, and how do we incorporate substituents and stereochemistry to the names. So let's talk now about carboxylic acid derivatives. So let's think of these compounds. Let's abbreviate it as, if we know that a carboxylic acid is this, I'm going to put an R here, and that's a carboxylic acid. So derivatives will have, this is similar, but I'm going to put here a Z atom or group. And let's see what's the nature of that. So in those derivatives, we're going to find the following. So if I replace the Z by a halide, and let's do this, for example, it is an acyl chloride. Oh, bad spelling. So yeah, again, what is chloride, but in general is halide. So acid chloride in this case. So that's one type of derivative. That could be, of course, fluorine, bromine, most commonly chlorine and bromine. Now, another derivatives of carboxylic acid, I'm going to replace the Z, this one here, I replace with a halide. Now I'm going to replace it another way. So I'm going to replace that Z, and I'm going to put here this. And now, let's make it bolder. Was kind of too light. Okay. So what I did was I replaced this by all of these. And altogether, this molecule is an anhydride. Yeah, so another derivative. One more. What we can do is now we're going to be replacing the Z by something else. That's something else this time. Let's see. We're going to do O, so OR. And now this is an ester. And I have the Z is now this. See, here it was chlorine. And another derivative of the carboxylic acids are this one I'm going to be replacing. This is going to be now a nitrogen, in this case with two H's. And this functional group is an amide. So now these are derivatives, but we can also have, consider in this group, not exactly the same structure, but we will have the chemistry of nitriles when we study carboxylic acids in derivatives. So that's a nitrile. And we know that, for example, if you have this, that's a salt. This is sodium cyanide. But when this functional group, it is in an organic molecule, we're going to call that a nitrile. Okay, now let's talk about oxidation state at the carbon that bears that C. So what I want you to see here, let's do the oxidation state here and here and here. Because when we consider reactions of aldehydes and ketones and so on, many reactions, sometimes we're looking at redox reactions. So when we say we have a ketone and say that I use lithium aluminum hydride, I will reduce that to a secondary alcohol. That's a reduction. Now let's do oxidation state to remember this one. If I have this reaction, the oxidation state of carbon, the central carbon here, is going to be, I'm going to do 4 valence electrons minus, and then I'm going to assign the electrons in the bonds to the more electronegative atom. So here, 2 and 4 electrons in the bonds to oxygen are going to be assigned to oxygen. And then this is carbon, and that's another carbon, so I'm going to split that in half. So 1 and 1. And same here. So now I need to count how many electrons are assigned to the central carbon, and I count 1 and 2. So the oxidation state here is 4 valence electrons minus 2 that I have assigned in that structure. That is a plus 2 oxidation state. Now we're going to do the same in the other structure. But here, remember that we have an H. That was not pictured. So in doing the same, assigning the oxidation state here, I'm going to start with 4 valence electrons. And then again, electrons and bonds are assigned to the more electronegative atom of the two in the bond. So I'm going to do this bond. All of the 2 electrons are going to be assigned to oxygen because it's more electronegative than carbon. And here, between carbon and hydrogen, carbon is more electronegative, so these 2 electrons I'm going to assign to the carbon. Now here, this bond is carbon-carbon, so I'm going to do half and half. And this is carbon and carbon, so half and half. So for the oxidation state, then, let's count how many electrons are assigned to the central carbon. I have 2 here, 2, 3, and 4. So 4 minus 4, we have an oxidation state of 0. So notice the oxidation number to 0 had decreased. So this is a reduction. And doing that recap in oxidation number to understand what's going on with carboxylic acid in derivatives. So let's do one oxidation state here at the, that could be acetic acid or anything that R means that is a carbon chain. So if I do the oxidation state here at this carbon, I start the same way, so say 4 valence electrons, and then electrons and bonds assigned to the more electronegative. So between this carbon and the oxygen, obviously oxygen is more electronegative, so I'm going to assign the 4. And same here, I'm assigning those 2 to the oxygen, those 2 in the bond. And here is carbon-carbon, so I'm going to split it even. So how many electrons are assigned to the central carbon? Well, only 1 here, because the others are assigned to oxygen. So oxidation state here is plus 3. So let's do that for the chloride. So I'm doing, these are the general formulas, say, for the carboxylic acid derivatives. So now let's do the acid chloride. Same, we're going to start. My starting point is my valence electrons. And then assigning the electrons to the more electronegative. Between these 2, it is oxygen taking those 4. Between carbon and chlorine, chlorine takes the 2 electrons in that bond. And here I split even. So what it is, how many electrons are assigned to a central carbon? So only 1, again. Because this 4 went to the oxygen, this 2 went to the chlorine. So now it's only 1. 4 minus 1 is a plus 3. So what we have here, plus 3, plus 3, same oxidation state. And let's do it one more time. For that ester at that central carbon, 4 valence electrons minus, and we're going to do the same thing, assigning electrons. This 4 go to the oxygen, this 2 go to the oxygen, this is split in half. So same thing, only 1 electron is assigned to a central carbon. So it's again plus 3. So all of the carboxylic acid derivatives have the same oxidation number at the carbon. So when we're doing reactions with these derivatives, there is no change in oxidation state if I go from an acid chloride to an ester, which we're going to be doing that in synthesis. So when it is in this family of compounds, carboxylic acid and derivatives, we don't have changes in oxidation state. If I go from this to that, or from this to that, from an anhydride to an amide, we're going to be doing those reactions. Lastly, let's try the nitrile. That looks slightly different, we know. So the oxidation state here, 4 minus, and then let's see. Nitrogen is more electronegative than carbon, so it's going to take the 6 electrons over there. And this is split even because it's carbon-carbon. So only 1 electron is assigned to the carbon. So 4 minus 1 is plus 3, same. So same oxidation state for the all the carboxylic acid derivatives.